Okay, we did not completely finish our discussion of span. So, clarification, I'm calling this 1.3b span, not because there's actually a section in the textbook called 1.3b span, but rather they decided to introduce a very important concept almost as a bookend to the section, which is a little weird. So we're going to talk about span, make sure we understand this because a very, very decent portion of the class requires knowing what span is. Sorry, I just got distracted by two red-tailed hawks flying through the. Okay. Let's actually recap the definition though, so that we know what we're talking about. So, recall what is span, and we didn't have much time to talk about the motivation for this definition, so let's do it now. If I had a set of vectors, and so what we learned in the previous lecture was that we can combine these vectors together with a scalar weight. So I can take a scalar and I can put that weight and multiply it with a vector. And if I have multiple vectors, I can just kind of keep adding all of those up in a chain. And we call those linear combinations of vectors. And so the question we ask is, well, say I had some vectors, maybe 3 or 4 vectors, and I wanted to know every single possible linear combination. Well, like how many types of vectors could I make through just linear combinations of these vectors? And that is basically the definition of span, is that total set of all the different types of vectors you can generate from mixing and matching linear combinations of a set of existing vectors. So the way we talk about this with math notation is if I have the span, actually, is it possible to make this thicker? Let's try this. The span, that might show up better on the whiteboard. Oh yeah, that's much better. Okay. The span of, we need some vectors to work with. So let's have p vectors, just a generic amount. Now what this really means is, again, what are all the different ways I can mix and match my set of vectors with scalar weights, and then put all of those into a set, and that total set of possible linear combinations is what I mean by the span. So what is a linear combination by definition? I need to give scalar weights to each one of these vectors and add them up together. So I'll do C1, V1 all the way through my P, CP, VP. And then the only condition we need to specify, so this tall bar in set notation is the words such that, basically just kind of like a condition or clarification on something beforehand. So C1, V1 through CP, VP, such that we need the C1 through CP to be just scalar values, in other words, real numbers. Okay, this is from what we call a linear combination. And so what we can really see is that a span is just a set of all possible linear combinations for that set of vectors. Okay, so that's our definition. And so here's an important note. If we ask, so asking whether a vector B, whether a vector B is in the span of some vectors V1 through VP, amounts to asking, so it's the same question, amounts to asking what? Okay. Whether the vector equation, whether the vector equation, what am I? Vector equation. Which we can write that, if you remember from class, we can write that vector equation as x1 v1 plus, and then so on and so forth, xp vp is equal to the coefficient vectors of the b. Has a solution. Has a solution. Or, and there's another way we can think of this, equivalently, asking whether the linear system with augmented matrix, which we can describe with, now these vectors become the pillars, or the columns of this matrix. So I have columns v1 through vp, oopsie, and then the b vector has a solution. Okay, so here is where it's going to be very important to learn how to read math, and I'm going to kind of show you how you can take something like this from the textbook and make sense of it. So, asking whether vector b is in a span. Okay, so let's anchor down our definitions. If b is in the span, and the span itself is the set of all the linear combinations of those vectors, then we can think of, if b is in this, that means I can write b as some linear combination of whatever these vectors are, okay? So what it means for b to be in the span of these vectors, by definition, is going to mean that there is some way I can generate b by mixing and matching the coefficients and weights of these vectors in the linear combination. Okay, so let's continue. So stating that amounts to asking whether this vector equation has a solution. Okay, now what is this vector equation really saying? It's saying I have weights, I'm calling them x now, like because I'm solving for it, x1 through xp, such that if I select the correct weights with those vectors, then I can spit out b. And you might think to yourself, yeah, that's literally what we just said. We just said that b being in this span by definition implies that there does exist some combination of scalar weights so that b we can generate b. And that vector equation is then just visualizing those solution of weights as x1 through xp. Okay, so a lot of these things in the textbook, it looks different. If these two sentences, and they look visually different, but you have to get past the cosmetic level of math. You got to go deeper. And a more mature view of math is to understand the concept that it's communicating fundamentally, and then realize that you can describe that same thing with a lot of different ways. So b being in this span, again, means there exists some combination of constants that I can multiply and make a linear combination to spit b out. The vector equation is just denoting that more explicitly. It's listing out the x1 through xp weights, these coefficients, multiplied by my vectors that spit out b. Okay, so they are equivalent statements. Or, and there's another way we can think about this. Equivalently, we can ask whether the linear system with this augmented matrix has a solution. Okay, so again, remember from the previous lecture that all of the different equivalent ways we could denote something. And so we talked about translating between the vector equation and the augmented matrix and all these things. Okay, so if we understand the relationship between this augmented matrix and its vector equation, then this last part is given, it's obvious. Okay? That being said, it's not obvious if you don't remember that you can relate an augmented matrix to its vector equation. But if you do have that part, then all three of these go together. Okay, so there's that. It's very important. And then now there is a geometric intuition. That's actually kind of nice. Geometric intuition. There is a really fantastic video animation done by a YouTube channel, 3 Blue 1 Brown. I'm going to put the link of that video in the description for this lecture, just because if you want, what I'm going to draw on this whiteboard is kind of pathetic compared to what his computer graphics can do. So if you're more of a visual learner and really want to see it, just go to that video and kind of skim through until he gets to the part where he's visualizing out what these spans are, because it's really beautiful and it might help. But if you're conceptual and you can pick it up from this, that's great. So let's explore this. So what is the span? We've talked about the definition a lot, but we haven't really just done something, so let's do one. Now, what's the span of one vector? Of one vector. And we'll start there. So, by definition, the span is going to be all the possible linear combinations of the set of vectors. In this case, the set of vectors is just one vector, but that's okay. So that means we have the linear combinations. Linear combinations of one vector. And so we could talk about this as just being some constant times v for all possible constants, right? Since we need all of the linear combinations, the set of all possible linear combinations, then we need to let C range over all R. Okay, so what does that really mean? If I take a vector, say I take this vector right here. This is our V vector. Now, visually, if I'm scaling this vector up, so say I increase C, maybe C is equal to 2, so I double, so it's 2V, okay? So then this would become, I could get the linear combination like this. What about if I keep increasing C? What if maybe I increase C to 3, right? So then we would have stretch out RV to here. And so we're really kind of just, imagine the C is like a dial, and we're sliding it up and down, and we're seeing all the different kinds of things that happen to V. And as we increase V, we're stretching out V as C increases. So we stretch out the vector V as C increases. So this is as C increases, we would be spanning more and more out like that. Now, if I start decreasing it, so if I now flip it to negative and start decreasing that coefficient, then I would start going in this way. And if I continue to decrease and continue to decrease and continue to decrease, so as C decreases over here. Now, I didn't hand draw it the most perfectly, but think about this. What geometric shape are we essentially sweeping out? What geometric shape is being spanned by one vector? And we see that one vector spans an entire line. The span of a vector, just a singular vector, is definitionally going to be basically all of these vectors that form a line in your space. So the span of one vector is a line. And we can write this with math, so we can say the span of just one vector, by definition, is going to be all of the vectors scaled. So all the vectors that we can get, if I take V and scale it by some scalar amount, which is in itself a line, geometrically. So this set of vectors, that is the span. Okay. What about the span of two vectors? Okay, so again, by definition, this implies that I want the linear combinations of two vectors. And so in the math language, I would say my span of two vectors, I can call them v1 and v2. This is going to be all the linear combinations. How do I make a linear combination with two vectors? Well, I need c1 with v1, and then I add that to the next one, c2 times v2. And specifically, I need c1 and c2 to be scalar, so real. Now, this is going to generate, well, I'm not going to tell you right now. So, let's think about this. If I take some vector, whoopsie. Maybe I take a vector, our vector v again. And now I'm going to introduce another vector, maybe this. So this is v1 and this is v2. So all of the possible linear combinations, and if you remember the head to tail that we talked about visually in the lecture, then first things first, we're still able to scale all along v1. And so v1 is allowed to increase. You can stretch out v1. So if you imagine a dial on like the C1 dial increasing, then this is increasing out. Similar behavior. So in this case, this would be C1 increasing. And if we started going down this way, like with the previous example, then obviously we have C1 is decreasing. But now we have another constant that could be scaling. What happens if V2 gets scaled up? So if V2 starts getting scaled up, it's going to be a similar behavior that we saw, just pointed in a different direction. So now this is C2 increasing. If I increase the constant that's multiplied by V2, it's going to get bigger. And if I flip it around and decrease it, in a similar sense, then now C2 is decreasing, right? C2 is decreasing. Okay, so that's only considering each of these individually. Now we need to think about what happens when they're acting together, like we're actually now combining these things. And so remember the head-to-tail method. I could easily add V1 and V2, and that's going to spit out, if I by the head-to-tail method, that. So now I can access this point. And I'll notice that at every single one of these heads, I can add V2. And not only can I add V2, I can add the scaled up versions of V2 as well. Not just the scaled up, but also the scaled down. Etc., etc., etc. And so what you see is how the question becomes, how many points can I access by just adjusting and sliding the weights and coefficients and adding in combinations of these two vectors together? Well, it sure looks like we're spanning this whole plane. All of these points we can access. And so, instead of a line, we have a whole plane. So, I could say that the span is a plane. If I have two vectors. Now, that's one way to do it, but you might be thinking, there is another outcome that could have happened. So notice that they were pointed in different directions. They weren't parallel to each other. So that was what enabled us to reach out off of just the line and sweep everything else out. That being said, that doesn't always have to happen. Let me show you how. Suppose now I have two vectors like this, v1 and v2. They are pointed in exactly the same direction. They're parallel. In other words, v2 is some scalar multiple of v1. And this is going to be a problem because now when I try to expand and scale up or shrink the C1 and C2, it really doesn't matter because no matter what, since they're pointed in the same direction, I'm still going to get stuck just sweeping out only points I can access on one line. They're pointed in the same direction. So one could think of that another way to express that visual intuition. If you have two vectors pointed in the same direction, that implies that you can write v2 as some scalar. So some scalar, I'll call that C0. Some specific scalar times v1. Well, this is a problem, right? Because if you can describe one of your other vectors as just being a scaled version of the other vector, in other words, a linear combination of the other vector, then really all you're saying is that this second vector isn't truly it's not contributing anything. It's just a member, it's in the span of your first vector. So if you get a vector that ends up just being a linear combination of another vector that you have, that doesn't make it new. It doesn't make it a contributing helpful vector. That just makes it a vector that's already existing in the span of the previous vector. And that's why you can have two vectors. Oopsie, I forgot to put an arrow over that one. You can have two vectors without it necessarily generating a plane. It will only generate a plane so long as this doesn't happen to us, where we get stuck with one of the vectors itself being a linear combination of the other. So watch that a few times. Make sure that makes sense. Think about it. Because if you can anchor that idea down and really think about it, a lot of concepts moving forward are just going to seem obvious. But if you rush past this and you really don't take the time to understand that, then it's going to feel a lot more arbitrary and random of why there's certain rules or why there's certain properties later down the road. Okay? So again, if I can describe, so say I have a set of vectors. So if I can describe one of those vectors as just a linear combination of the other two, or another vector, then by definition that makes that vector just a member of the span without it. In other words, we don't need it to actually generate everything. So I could completely eliminate v2 and the span is exactly the same. And if I'm able to do that, that means that this was kind of unnecessary. We're going to put terminology to that later, so I'll kind of hint at it now. If we're able to do that by eliminating one of these vectors and it doesn't affect the span, so if it's some scalar multiple or something like that, if it's in the span, call that being linear dependent vectors. These vectors are linearly dependent. They depend on each other. v2 depends on v1 because so long as v1 exists, I can scale v2. I can scale it and get v2. Compare that to v1 and v2 here, where the v1 and the v2, they are not parallel. They do not point in the same direction. There's basically what that means. I can't just take v1, I can't multiply it by a scalar and somehow get v2 out of it, okay? They are not dependent on each other. They are independent from each other. So we call this linear independence. So we'll get to that more later, okay? Let's see. That's really all I wanted to say about that. To make things a little more tactile, so that for the engineers, you've been doing spans your entire time doing engineering. And here's why. The trivial span of the Cartesian plane comes from two vectors that are trivially independent from each other, and you know them. You're very familiar with them. If I take the span of I and j, so I hat, one and then j hat, this is all of the linear combinations I can get. C1 with I hat, C2 with j hat. You might think of that as x I hat, y j hat, such that C1, C2, you can think of that as xy are real. And basically, we know what that is. That's just the plane. That's R2. Like, if I take, here's x1, x2. If I take I hat, and I take j hat, and I take all of the possible combinations of moving one over and up one over one, up one, then yeah, I can access every single point in the plane, obviously, just by nature of adding and subtracting necessary combinations of these fundamental unit vectors. And so these fundamental unit vectors form, well, we'll later call it basis, but for now you just need to understand that the span of these two will cover R2. It's the trivial span of R2. And then, of course, if I took span of I hat, j hat, k hat, that's just all the linear combinations, all the points you can access with those three fundamental vectors. And so, again, that's going to trivially span all of three-dimensional space, as we know. Okay? So it's another perspective to think about those things. So we'll talk more. You'll be hearing a lot more about all of this in future lectures, but this is a good start for the concept of span and why we have it.